Morning, everyone. Okay, so it's already 10, and I think we should get started. Okay, so hope you all had a good break on Wednesday. So as you can see from the midterm, I mean, I don't typically want to give you something special during the exam. So if you really have gone through your homework quite carefully, you should be able to answer them in sufficient time. Okay, I know that having 6 problems is a little bit tight in time, but if you're really, familiar with the questions or with the homework problems, I think you should be able to answer most of them at least. All right. So this class, we're going to continue on the sulfur dioxide control. So last class, we mainly introduced how we could control sulfur dioxide. All right, so let's do a quick recap. Right, so basically, we mentioned that for sulfur dioxide, it is an important air pollutant. That's why it's regulated as the one of the 6 criteria air pollutants. Right. So we mentioned that there are 2 major sources of the sulfur dioxide. So one is from the oil refinery and the other is from the coal-fired power plants. The oil refinery occupies 1/3, and then coal-fired power plant occupies 2/3, right? And we say that to control the sulfur dioxide, we have to come up with some control methods. And for each of them, they're using a special technique. For example, for the oil refinery, we use the fuel desulphurization. So what that means is that before we distribute the oil products to the customers or the gasoline to the customers, we'll first try to extract all of the sulfur out of it, right? And that is by using this Klaus process, which is using the hydrogen sulfide to react with the sulfur dioxide, and we can get solid sulfur. And we were saying that just by using the solid sulfur coming out of the oil refinery, we can cover 90% of the sulfur supply in the United States, which means that on one hand, this chemical engineering process is very useful, but on the other hand, we really use a lot of oil, right? So, with this process, we could effectively control the sulfur dioxide emission coming out of the oil refinery. And in terms of the coal-fired power plant, we will use the flue gas desulphurization. So the reason why we cannot use the fuel desulphurization for coal-fired power plant is we were burning coal particles, but the coal particles are solid, right? So for solid particles, it's going to be difficult for the let's say the hydrogen sulfide to get inside, not hydrogen sulfide, but hydrogen, right? It's going to be difficult for the hydrogen to get into the core of the coal particle to extract the sulfur out. So that's why we tend to deal with it after the combustion. And also the advantage for the flue gas desulfurization is that we typically centralize all of these coal in the coal-fired power plants. So that's easier for us to emit everything first and then deal with them before we basically release the flue gas, the treated flue gas. All right. And in our last class, we also went over some sulfur dioxide control devices. For example, we could have the limestone scrubbing. So what the limestone scrubbing it means is that we're going to introduce the flue gas that contains, let's say, these toxic gases, especially sulfur dioxide. We're going to send it into this scrubber here. And then at the same time, we're going to introduce a solution. So more exactly speaking, it should be a slurry, right? So it's mainly composed of limestone and water. And since limestone does not dissolve into the water, so it's more like a slurry that contains some solid inside, some water inside. Most of them is just water. And then we're going to spray these droplets from the top of this scrubber tower here. So what happens is that the sulfur dioxide is going to react with the calcium carbonate, right, to form calcium sulfite. Okay, so this is sulfite, right? And then carbon dioxide. So this is a chemical reaction going on through this process. So basically you have a droplet. Let's say if we zoom in, right, you're going to have a droplet that contains some solid inside, and then the sulfur dioxide molecules, gas molecules, are going to get absorbed into the solution, into the droplet, and further react with the calcium carbonate inside. And since we were forming calcium sulfite, okay, calcium sulfite is not stable enough, and also it has a pretty high solubility. It can basically dissolve in water. So that's why we're going to inject oxygen into the tank at the bottom. Okay, so the droplet falls down to form this solution here, right? And then we're going to introduce oxygen inside. So what happens is that the calcium sulfite is going to react with oxygen to form calcium sulfate. Okay, so the calcium sulfate has a relatively low solubility, which means that they're going to form solids, right? And it's not going to get dissolved in water, and then it's just going to settle down. So that's why at the bottom of this tank here, we're going to collect a lot of liquids here, but still water is going to be a major component of these products here. And we also call these exhaust here as the sludge. Okay, so there's some difference between the slurry and the sludge. So slurry contain more water, sludge contain less water. Okay, and then basically this is a chemical reaction that's taking place. And we could also have other types of scrubbing systems, for example, the lime scrubbing. So instead of using the limestone, which is the calcium carbonate, we can use calcium oxide. So the calcium oxide is going to react faster with the sulfur dioxide. So if you're dealing with the flue gas that has a higher sulfur dioxide concentration, right? If it's more concentrated, you may want to use the lime scrubbing to more effectively collect those toxic gases. And we can also have the lime spray drying, right? So for the lime spray drying, what it means is that we're going to reduce the size of the droplet. We're just going to make it smaller. So when you spray these droplet down, it's not going to form this solution at the bottom. So instead, it's going to settle down, and then as they evaporate, they're going to change into particulate matter, right? And then go out with the flue gas. Okay, so basically the spray drying process is going to remove the sludge that's forming at the bottom of the tank here. And because of that, we're basically forming a lot of particulate matter here, and we have to deal with the PM control devices. So the idea is quite similar to the direct injection method, where we're using the chona or the lime, right? And then basically you're introducing, I'm not sure if I have it here, but you're introducing these solids into the flue gas to let it react with the sulfur dioxide without the help of water. So in this way, you can basically remove those sulfur dioxide, but at the same time, you're forming particulate matter. And that's why you have to deal with those PM, okay? But in this class, I mean, especially in the classroom, we're going to mainly deal with the limestone scrubbing, okay? About the design, what are the design parameters we need to calculate. But I want to mention that for your team project, you have to design the direct injection method. Okay. So our textbook has some contents on that. So I have to say that the direct injection is a relatively newer method because it's more compact. It saves the entire space for the scrubber. So basically, you're just introducing solid into the flue gas. But in this class, we're just going to focus on the limestone scrubbing. All right. So then we may have the question: what are the design parameters for the limestone scrubbing or for the sulfur dioxide control? So I would say that the most important two parameters that we're interested in is how much limestone we have to provide in and how much gypsum we're getting out. Okay. These are the important parameters to a coal-fired power plant or for other industries because they have to come up with a transportation system, right, to basically make sure that they have enough of the sulfur dioxide, they have enough of the limestones to neutralize these acidic gases, right? And they also want to know how much gypsum or how much sludge they're forming, because if they cannot remove these solids effectively, then this tank here is going to get overloaded, right? So I would say these are the most important parameters, and these are also the only parameters we're interested in designing these systems. Okay, so how do we find these consumption rates? Okay, so I'm giving a very simple scenario here. Okay, so for example, if we have a coal-fired power plant and we know that it's emitting 64 tons of the sulfur dioxide per day. So how do we know that? I think you have the exam problem of calculating the sulfur dioxide emission rate from a coal-fired power plant, right? If you know the capacity, let's say 500 megawatt, you know the heating value, you know the sulfur content, you should be able to calculate what is emission rate of the sulfur dioxide, okay? So let's say that if we know that this power plant is emitting 64 tons of sulfur dioxide per day. And then let me ask you, how much calcium carbonate do we need to neutralize these sulfur dioxide per day? Okay, so this is I would say this is a relatively simple stoichiometry problem. If you check the chemical reaction that we wrote here, we know that the sulfur dioxide is reacting with the calcium carbonate as a 1-to-1 ratio in terms of the molar ratio, right? What it means is that if we want to collect, if we want to neutralize 1 mole of the sulfur dioxide, we have to provide 1 mole of the calcium carbonate, okay? So now it just comes to the question of how many moles of the sulfur dioxide we're dealing with. So let's say that we're not looking at tens for now, we're looking at grams, okay? So if we have 64 grams of sulfur dioxide, and we know that the sulfur dioxide is reacting with the calcium carbonate to form calcium sulfite and carbon dioxide, okay? Everything is 1-to-1 ratio, but I also want to point out that it doesn't matter which carbonate we're using. If you decide to use the magnesium carbonate, it's still going to react with the same molar ratio, right? You're going to form magnesium sulfite and carbon dioxide, okay? So basically, what's involving in this reaction is the carbonate ions, okay? So in order to basically write that out, what we can do is we can just remove these calcium here. So what really happens is that the sulfur dioxide is reacting with the carbonate ion to form sulfide ion and carbon dioxide, and both of them are reacting at a 1-to-1 molar ratio. Okay, so now if you know what is the mass of the sulfur dioxide, right, we can calculate what is the number of moles for the sulfur dioxide. So that is the mass of sulfur dioxide divided by the molecular weight of sulfur dioxide, right? That's 64 grams. And in terms of the molecular weight, we know that the sulfur is 32 grams per mole, right? Oxygen is 16, but we need to multiply that by 2, okay? And this turns out to be 64, okay? That is simple enough, 64 gram per mole. And that's just exactly 1 mole, okay? So 64 grams of sulfur dioxide is 1 mole of sulfur dioxide, okay? And because of this 1-to-1 molar ratio, we know that, so if we want to react with 1 mole of the sulfur dioxide, we need to provide 1 mole of the carbonate ion, right? What it means is that we need to provide 1 mole of the calcium carbonate, right? So if we know the let's say the mole number of moles for the calcium carbonate, then we can calculate what is the mass of the calcium carbonate. That is just this N here multiplied by the molecular weight, right? So what is the molecular weight of calcium carbonate? So that is, let's say, this calcium is 40, right? Carbon is 12, and then oxygen is 16, but you need to multiply that by 3, right? So if you add them together, that's exactly 100 gram per mole. Okay, so if you multiply 1 mole by 100, that's going to be 100 grams, right? So basically, in order to react with 64 grams of sulfur dioxide, we need to provide 100 grams of the calcium carbonate. So if you know that we have to neutralize 64 tons of the sulfur dioxide, we need to provide 100 tons of the calcium carbonate. Okay, so this is, I would say this is the most simple condition for a let's say the scrubber design problem. Okay, so we're assuming that we're dealing with pure substance. Okay, but the actual scenario is that the limestone is not completely made of calcium carbonate. So as I pointed out in this bullet point here, so limestone is made of calcium carbonate, magnesium carbonate, and some inert materials, okay? But the thing is still similar because we're trying to deal with the carbonate ions instead of the others, okay? So we don't need to get too worried about that, but we can go through this process in the example problem later on, okay? So this is basically trying to find out what is the feed rate of the limestone, right? As we calculate out, we're going to need 100 tons per day of the calcium carbonate, right? And this is the feed rate. And then what about the product rate or the sludge production rate, okay? So for example, the second question is asking how much sludge is being formed, assuming that it's made of 50% water and 50% solid, okay? So this is again based on the stoichiometric ratio, right? So if you write out this chemical reaction equation again, right? Sulfur dioxide reacting with calcium carbonate to form calcium sulfite first, and then the carbon dioxide. And then we know that in the limestone scrubbing, we also oxidize the calcium sulfite to calcium sulfate, right? So basically, the solid that's being formed at the bottom of the scrubber is calcium sulfate. So as we already find out that for 64 grams of these sulfur dioxide, we need 100 grams of the calcium carbonate, right? So everything is reacting at a 1-to-1 ratio. Okay, so what it means is that if you have 1 mole of the sulfur dioxide, you're going to eventually form 1 mole of the calcium sulfate, which is the solid that's forming at the end of this scrubber here. Okay, so then we can directly calculate out what is the mass of the calcium sulfate. So that's going to be the number of moles multiplied by the molecular weight of the calcium sulfate. As we mentioned, the number of moles for the calcium sulfate is exactly the same of the same with the number of moles for the sulfur dioxide, which is 1 mole, right? So that's going to be 1 mole multiplied by the molecular weight of the calcium sulfate, right? So that if we just do this calculation again, right? Calcium sulfate. Here you have 40, here you have 32, and then you have 16 multiplied by 4. Okay, so it turns out that this answer is 136. Okay, so basically you're going to multiply that by 136 gram per mole. Okay, so you're forming 36 grams of the calcium sulfate. Okay, so if we just look at this this emission rate again, right, we're forming 64 tenths of the sulfur dioxide, then it means that we have to generate 136 tenths of the calcium sulfate. But this is not the end yet, because if you look at this problem, it says that the sludge is made of 50% water and 50% solid. So we need to consider the other 50%, which is exactly the same as the mass for the calcium sulfate, right? So the mass of the sludge is going to be equal to the mass of the calcium sulfate plus the mass of water, right? We said that each are representing 50%. So that's just 2 times of the mass of the calcium sulfate. So that turns out to be 272 tons per day. Okay, so this is a sludge formation rate, right? So as I said, everything is based on the stoichiometry. And this is actually the most simple scenario. We're making a lot of assumptions here. For example, we were assuming that the limestone is pure, right? But actually in the real, let's say the power plant sulfur dioxide control, we cannot basically, we cannot deal with the sulfur dioxide with exact stoichiometry, okay? So if you think about this reaction process here, so you have a droplet, and then you have solids inside, and then you have sulfur dioxide that tries to get into the solid, tries to get into the liquid and react with the solid. So this reaction here is actually quite slow, okay? And because of that, we actually need to provide more limestone, okay, or more calcium carbonate to neutralize these sulfur dioxide gas, okay? So in actual engineering, right, we cannot provide the exact amount required by stoichiometry. We can provide, let's say, 10% or 20% more of the required limestone. And also, even if we do that, we probably still cannot remove all of the sulfur dioxide because this reaction here is very difficult to happen. Okay, so we could set up a standard. Let's say that our goal is to remove 90% of the sulfur dioxide. Well, at the same time, we have to provide more limestone to neutralize those 90% of the sulfur dioxide. Okay, so we're going to deal with this more sophisticated design problem with the next question here. Okay, so this is the sulfur dioxide scrubber design problem on your textbook. And I have to say that this problem really look like your team project. So what I really like about this problem is that they provide this table here. Okay, so what this table shows is the flue gas composition and the flue gas, basically the flue gas flow rate out of the coal-fired power plant. For example, it provides the total flow rate, right? It also provides you the mass flow rate of the flue gas. But what's more important is that they give out this breakout of all of the air pollutants here. For example, you have particulate matter, carbon dioxide, hydrogen chloride, nitrogen, oxygen, sulfur dioxide, and moisture, okay? So basically you have the mass flow rate, right? The pound per hour, you can easily convert it into tens per day, right? And then you also have the mole percent. Okay, so this is a nice breakout of all the chemical compositions and the flow rates of these gas species in the flue gas. Okay, I would expect that in your team project, you come up with a similar table here. So I'm not only saying about the format is similar, but also if you look at your problem, it's designing a coal-fired power plant of several hundreds of megawatt. Okay, but if you look at this same problem here, it's showing the gas composition of a 500 megawatt power plant. So in terms of capacity, they're on the similar order magnitude, right? The coal composition is not going to be very different. So because of that, for your flue gas flow rate, I would say that they should also be on the similar order magnitude. Okay, so we cannot, let's say that for the sulfur dioxide, if you come up with a value that's, let's say, just 80 pound per hour, you know that definitely there's something going wrong here. Okay, because we're dealing with a similar scale of the coal-fired power plant, right? The coal composition is similar. We should have something that's quite similar in terms of order magnitude there. Okay, so I'm not sure if you have started to look into this problem, the team project. I think definitely after this class, you should be able to complete all the engineering calculation there. Okay, so the rest of them is just going through the cost analysis. So I think now is a good time to get started on your team project. And as you can see, we don't have quite many, we don't have as many homework as before the mid-semester, okay, before the midterm. So I would say that try to spend more time on your team project now. Okay, so if we come back to this question, we're trying to design a sulfur dioxide scrubber system. Okay, so this is what the problem states, right? Let's say that the scrubber, we only assume that it can remove 90% of the sulfur dioxide. So we're not trying to remove everything, okay? Because that's not possible because the reaction is too slow. So we set our goal to remove 90% of the sulfur dioxide, which is the flow rate here. And also the complete removal of the hydrogen chloride. So the hydrogen chloride is more toxic, but at the same time, it reacts faster with the, let's say, the limestone or the trona. Okay, so we could set the goal of complete removal of the hydrogen chloride. So now it wants us to calculate the feed rate of the limestone. Okay, so if you compare this question to the question that we just talked about here, right? In order to control 64 tons of the carbon dioxide per day, how much calcium carbonate do we need? So we're asking similar questions. It's just now that it's getting a little bit sophisticated that we need to set up a different goal, right? 90% removal and also the complete removal of the hydrogen chloride. So then we need to calculate the feed rate of the limestone. So the second part of the question is saying that we assume that 60% of the sludge mass is water, right? For the previous problem, we assume that 50% is water. So now 60% of the sludge is water and all the sulfite are oxidized. Basically the calcium sulfite is oxidized into the calcium sulfate, right? And it wants us to calculate the production rate of the sludge. So this is also a very similar question that's being asked here. But now things are getting a little bit sophisticated, but at the same time, we have to make assumptions to the composition of the limestone, okay? So for example, here, the problem says that the limestone now is not pure calcium carbonate anymore. It's made of 94% calcium carbonate, 1.5% magnesium carbonate, and then 4.5 inert. Because if you just look at limestone, basically a rock in there, right? It's not a pure substance. There's always some inert that cannot react with anything, right? And actually there are far more complicated or far more chemical species in there. And I would say that even 94 and 1.5 is already a simplified composition there. But here we could just assume that the limestone is made of these chemical components, okay? And then this problem also says that the alkalinity is supplied, okay? So basically alkalinity is the reactant that neutralize these sulfur dioxide and hydrogen chloride, okay? So it says that the alkalinity supplied is equal to 1.1 times the stoichiometric ratio. So basically we're providing 10% more of the limestone, of the required limestone to the reactor to achieve this complete removal or the most of the removal of these acidic gases, okay? So these are the complexities in this problem, okay? And basically we have to, I mean, in real sulfur dioxide scrubber design or your, let's say, trona injection or limestone injection problems, you have to consider these complexities, okay? So now let's look at this question here. So basically the first question is asking us, what is the feed rate of the limestone that's required to remove, let's say 90% of the sulfur dioxide, and then the, and also the complete removal of the hydrogen chloride, okay? So if you think back on how we solved the question on in here, right? So what we did is we first try to find out what is the stoichiometric ratio, right? So we have to go back to the chemical reactions, right? How much of the, how many moles of the calcium carbonate are required to remove the sulfur dioxide? And at the same time, how many moles of the calcium carbonate are required to remove the hydrogen chloride? So we need to first write out what are the chemical reactions, right? So we have the sulfur dioxide. We have the sulfur dioxide react with the let's say, not calcium carbonate. Let's directly say that carbonate ions, right? So as we said, the reaction is really taking place between the acidic gases and the carbonate ions, right? So for this reaction, it's forming sulfide ion and the carbon dioxide, okay? So similarly for the hydrogen chloride, it's also reacting with the carbonate ions, right? And you are forming basically chloride ions and carbon dioxide and water, okay? But for this second reaction here is not balanced yet, right? We have to find out what are the coefficients before each chemical components here. So we know that it's reacting with 2 chloride ions, right? And in this way, if you check, we have 2 chloride on the left, 2 chloride ions on the right. We have 2 hydrogen, right? And then 3 oxygen here, okay? 2 oxygen here and 1 oxygen here. So now the reaction is balanced, right? So now we know that in order to neutralize 1 mole of the sulfur dioxide, we have to provide 1 mole of the carbonate ion. And in order to react with 2 mole of the hydrogen chloride, we need to provide 1 mole of the carbonate ion. So basically, if you want to remove 1 mole of the HCl, hydrogen chloride, you need to provide 0.5 mole of the carbonate ions, right? So basically, from this these 2 equations here, we can find the stoichiometric ratio. So if you just think back how we deal with that simple question there, we need to first find out what is the molar flow rate for the sulfur dioxide and hydrogen chloride, right? Remember that we had 60 tons per day. So that turns out to be what? It requires 100 tons of the calcium carbonate. So that is done by 64. That is done by dividing these mass by the molecular weight, right? 64 gram per mole, right? So we need to find out basically how many molar, let's say the molar flow, what is the molar flow rate for the sulfur dioxide, okay? So our target is basically to neutralize the acidic gases. Okay, so we have to use the carbonate ions to neutralize these. Okay, so we need to first find out what is the basically what is the molar flow rate or the mass flow rate of the sulfur dioxide. For example, the mass flow rate of sulfur dioxide is by using this value here, 31080. And our goal is to neutralize 90% of the sulfur dioxide. Remember here, 90% removal efficiency of the sulfur dioxide. And although this table here is showing you the imperial units, everything is shown in pounds, I would recommend you that we still convert it into standard units. That's more convenient when we do the molecular weight analysis. Okay, so basically you multiply 0.45 kilogram per pound. Right here, I'll put in pound per hour. Okay, and then it turns out that the mass flow rate of the sulfur dioxide is 12587.4 kilogram per hour. So I ask you to bring a calculator, so you can also type in these values to see if you're getting the same results here. Okay, and if you want me to slow down a little bit, please do say so. Okay. So basically, we need to first find out what is the mass flow rate of the sulfur dioxide that we have to deal with. Okay, and similarly, we need to find out what is the mass flow rate of the hydrogen chloride. That is 432 pound per hour multiplied by 0.45 kilogram per pound. That turns out to be 194.4 kilogram per hour. Okay. So now with the mass of the sulfur dioxide and mass of the hydrogen chloride, we could find out what is basically the molar flow rate of the sulfur dioxide and the hydrogen chloride. Okay, so basically you have you can directly use the mass flow rate divided by the molecular weight of the sulfur dioxide, right? And similarly, you have NHCl equal to MHCl divided by the molecular weight of the HCl. Okay, so the sulfur dioxide has a molecular weight of 64. And then the hydrogen chloride has the molecular weight of 36.5 gram per mole. Okay, so with these molar flow rates of the acidic gases, we can find out what is the required, basically the carbonate ions required per hour. Okay, so we know that from these two reactions here, so in order to react with 1 mole of the sulfur dioxide, we need 1 mole of the carbonate ion. In order to react 1 mole of the hydrogen chloride, we need 0.5 mole of the carbonate ions, right? Basically, for the sulfur dioxide, right, that is going to be M SO2 divided by the molecular weight of SO2, right? Exactly the same thing here, right? And then we need to multiply that by 1, which is 12587.4 divided by 64. Okay, so one thing that I want to point out is that in this calculation, we were using kilogram in the numerator and gram in the denominator, right? So basically, we also need to multiply this thing by basically 0.001 gram per kilogram. Say kilogram per gram. Okay, so 0.001 kilogram is 1 gram. Okay, so by plugging in the values, you can find out that the molar flow rate that's required for the carbonate ions is 196,671 mole per hour. Okay, so in order to neutralize the sulfur dioxide, we need this amount of carbonate ions into the system. Okay, and for the hydrogen chloride, we need MHCl molecular weight of HCl, multiply that by 1/2. So the reason behind that is basically in order to neutralize 1 mole of the this reaction here, in order to react 1 mole of the hydrogen chloride, you need 0.5 mole of the carbonate ions, right? So for that, you can find out this 194.4 divided by 36.5 multiply 0.001. That's 2657. Okay, so basically these are the carbonate ions that are required to neutralize the sulfur dioxide and the hydrogen chloride. Okay, so then we can find out the required carbonate ions, right? So that's going to be 196,671 plus 2657. That is 199,328 mole per hour. Okay, so this is the required carbonate ions. And then for this problem, it says that in order to let it fully react, we need to provide 10% more of the carbonate ions, right? So 1.1 times of the amount required by stoichiometric ratio. So what it means is that basically the actual carbonate ion that we provide to the system is going to be 199,328 multiplied by 1.1, which is 219,261 mole per hour. Okay, so this is the amount of the carbonate ion that we need to give to the scrubber. Okay, so then basically this is our target, right? We need to provide the limestone that can provide this amount of the carbonate ions. So what about reality? So in reality, we have a limestone that is not pure at all, right? Let's say that we have 1 bar of this limestone here. So we know that based on the problem, right, it's assuming that 94% is calcium carbonate, 1.5% is magnesium carbonate, and 4.5% is inert. Okay, so basically if you draw it on this 1 bar here, you have 4.5 being as inert, right? 1.5%, that's magnesium carbonate, right? And then the remaining 94% is calcium carbonate. Okay, so how much of the limestone should we provide to the system? Okay, we know that what is the actual amount of calcium, what is the actual amount of carbonate ions we need, right? We just need to find out what is the total mass. Okay? To make the things a little bit easier, let's assume that we have 100 grams of the of this limestone here. Okay, let's try to analyze for this 100 grams of limestone, how many carbon ions can it provide? Okay, so if you have 100 grams of the limestone, so I saw the question posted by Mackenzie, what does the red say for reality? So I didn't quite understand your question. You can unmute yourself and.
Yeah, so you have 4.5% something, but I can't read what the something is.
Oh, the 4.5 is inert.
Inert, okay.
Yeah, that's the inert. So basically in the limestone, you have something that's not reacting with the acidic gas at all, right? You don't have a stone that is made of pure substance in there. Okay, so what we are trying to do is trying to look at how much or how many carbonate ions it can provide per unit mass of the limestone. Because here we know what our goal is. We need to provide this amount of carbonate ions, but we don't know basically how much carbonate ions it can provide by the limestone here. So this is the process of trying to get that out. Okay. So if you have 100 grams of the limestone, you know that you have 94 grams of the calcium carbonate. You have 1.5 gram of the magnesium carbonate, and then 4.5 gram of the inert. Okay. But based on the mass here, you can find out actually how many carbonate ions are there, right? So for this 94 grams of the calcium carbonate, you can just divide it by the molecular weight of the calcium carbonate, right? So 94 divided by 100, that's 0.94 mole of the calcium carbonate or the carbonate ions, right? And then for this 1.5 gram of the magnesium carbonate, so that's 1.5 divided by 84, which is 0.0178 mole of the carbonate ions. Okay. So if you add these two together, you're going to have 0.957 mole of the carbonate ions. Okay, so basically what we're trying to do is we're trying to find basically a slice of the limestone. Let's assume that is 100 grams to find out how many carbonates ions they can provide to the reaction. Okay, so it turns out that this is 0.957 moles of the carbonate ions. So now we have the actual, basically the target for the carbonate ions, the total amount of carbonate ions. We have the reality, right? 100 grams of the limestone can give us this amount of the carbonate ions. Then we can find out what is the mass of limestone. That is just the total mass required, right? Divide that by 0.957 mole of the carbonate ion per 100 grams of the limestone, and then multiply that by 100 grams of the limestone. Okay, so basically it's taking the ratio between our target and the amount of carbon ions that can be provided per unit mass of the limestone, and multiply that by the unit mass. Okay, so the final answer you can get is 22,911 kilogram per hour. Okay, so this is the total amount of limestone that's required to put into the limestone scrubber system. Okay, so you can find that this calculation here is indeed quite sophisticated. But if you really look into the calculation here, I have to say that it's somewhat similar to what we have done earlier for this simple question. Right? If you remember this simple question, in order to control this amount of sulfur dioxide, how much calcium carbonate we require are required to put into the system, right? It's pretty much a similar thing. We need to first find out what is the mass flow rate, right, for these acidic gases, convert it into the molar flow rate. And based on the stoichiometry, we need to find out what is the required carbonate ions for this system. And of course, you need to consider the extra amount of carbonate ions to make the reaction more complete, right? And then we need to look at what we have from this limestone here. So this limestone is quite complex in terms of its chemical composition, but we can find out per 100 grams of the limestone, how many carbonate ions can it provide, okay? And then we divide this total number of the carbonate ions by this unit number of the carbonate ions to find out what is the mass required for the entire system, okay? So I know that the calculation is a little bit complicated than before, so this lecture is also recorded, and we can briefly go over this calculation or this idea on our Monday class. Okay, so we'll be back in the classroom to show basically how this how we do, what's the idea that we do this calculation. We'll try to work out the second part of the question. All right, so feel free to let me know if you have any questions. Okay, thank you. So Mitch, are you still there? Yeah, so I haven't graded the exam yet. So hopefully next week, okay. Next week, I'll try to post the results out.